So we left off on this slide here going over the inverse square law and how actually changing the distance between two objects has a much larger impact on the force of gravity than changing the mass does because of that goofy square. So we went over the fact that when you double the distance, you actually get 4 times smaller gravitational pull. Tripling the distance between them gets 9 times smaller. Quadrupling the distance, 16 times smaller. We'll look at that in some actual examples here. Now in your notes, you're going to see the answers, so I'm going to walk through these anyway. It's our check for understanding. Historically, I've had kids really struggle with this lesson, so if you need to rewatch this several times, there's no shame in that. It says, our first question, this is slide number 17. Suppose that two objects attract each other with a gravitational force of 16 newtons. So we know the answer, F is equal to 16 newtons. If the mass of one object was doubled and the distance between the objects remained the same, then what would the new force of attraction between the two objects be? Well, in our equation, it's ugly, remember, F equals G times M1, M2 divided by D squared. It's ugly. G is never going to change, and because we're only asking the relationship here, you don't actually need to use that in this equation. I will sometimes have you punch that in, and I'll remind you of when you need to do that. But for now, we just want to see what impact does this change have on our original 16 newtons. Okay. We said that if you change just one of these, it's going to be a proportional change. So if you double one of them, it should double the force. If you quadruple one, it should quadruple the force. If you did that to 2, it's obviously going to even have a greater impact. But in this case, we said that we doubled one of the masses. And so what would that do to our overall force? It should double it. And so that's where we get that answer of 32 newtons. Okay, I'm going to copy this so that we always have it to see on our slides. The next one says, suppose that two objects attract each other again with that same force of gravity of 16 newtons. If the mass of both objects were doubled now and the distance is unchanged, what would be the new force of attraction? Well, if you double both, really what we're doing here is we're quadrupling the overall number. Doubling both masses are in the numerator portion of this equation, quadruples the overall answer. So 16 times 4 should give us that 64 newtons. So it's a much stronger attraction when the masses are larger. Okay, we're always kind of starting with the same 16 newtons, it looks like. Suppose that two objects attract each other with that 16 Newton force. If the distance between the two objects is doubled, what is the new force of attraction between the two objects? Remember, separating the objects more weakens the overall attraction, but it's weakening it in a squared fashion. So if we, let's see, what did it say here? The distance doubled. Really, it's distance squared. So 2 squared, it should give us 4 times smaller attraction. 4 times smaller is another way of saying, 16 divided by 4. 16 divided by 4 gives us that 4 Newton pull. So it has a dramatic effect on it, much greater actually than changing masses. Okay, hear me now. Changing distance has a greater impact than changing mass on that gravitational pull. Let's do another one here. We've got that 16 Newton attraction between two objects. Oopsies. If the distance between the two objects, is cut in half, meaning now we're moving the objects closer together, what is the new force of attraction between the two objects? Well, now, rather than separating them, making them weaker, we're getting them closer together, which is going to be much stronger. So really, we've gotten them twice as close together, if I can say that properly, twice as close together than they originally were. But it's squared, remember, distance is always squared. So really, we're looking at an increase by a factor of 4. 16 times 4 gives us that 64 Newton force. Bringing them closer together really dramatically increased their attraction, which again, it has a much greater impact than simply changing the mass. This is a lesson on relationships in a very messy equation. I will go over some problems with you where you actually have to give me that ugly number, the exact number of newtons. But I just want to make sure that you've understood how the overall force of gravity is affected when we do things like double a mass, double both masses, change the distance between them. And so you're really going to want to reference these examples quite a bit before we actually take our test, okay? If you have questions, bring them up in class, but I'm going to wrap this lesson up here. Thanks.